In this session, we are going to deal with PWM programming in STM32 F446 microcontroller. So what is the function of a PWM? PWM, it is generally used for controlling the speed of a motor. PWM stands for pulse width modulation. So these are the examples of few PWM signals with varied duty cycle. So here you can see the duty cycle is 25%, here it is 50%, here it is 75%, here it is 100%. So what do you mean by duty cycle of a PWM? So whatever PWM you are taking, for a PWM, two parameters are there. One is known as a time period. So let us take from here to here, it is known as time period of a PWM. So in this example, all the four PWMs are having same time period. And the second parameter is known as duty cycle. So what do you mean by duty cycle? Duty cycle is nothing but on time divided by time period into 100%. So on time divided by time period into 100%. So here you can see that around 1/4 of the time period it is on. That is why it is known as it is having 25% duty cycle. Here almost half of the time period it is on. So it is showing 50% duty cycle. Here 75% duty cycle. And the last one, for the whole time period it is on or it is high. So here it is said to have 100% duty cycle. So if you are giving this 25% duty cycle PWM waveform to a motor or to the driver circuit which is driving the motor will be on for only 25% of the time period. Remaining time it will be off. That means the motor will be rotating in a slow speed. But if you are giving the 75% duty cycle PWM to the motor, 75% of the time period it will be on and only 25% will be off. That means motor will be rotating in higher speed. And if you are giving this last waveform, for the whole time motor will be on and it will be operating in the rated speed or in the maximum speed. So by giving different types of PWM, you can control the speed of a motor. So this is how the PWM is generated in STM32. In one of the lecture we have seen that how to generate a delay using timer. So here for PWM generation also, timer is acting as a time base, right? So normally for a timer what will be happening? The timer counter will be incrementing. Whenever it is getting a clock, it will increment from 0, 1, 2, 3, etc. up to the value which is stored in timer auto reload register, right? When the timer counter is reaching the value stored in auto reload register, it will roll over back to 0. And when that rollover is happening, particular flag will be set, right? That is how the timer is configured and timer working is carried out. So it will start counting from 0 to ARR. When it is reaching ARR, it will again roll back to 0. So this process will be continuously done, right? So for the PWM generation, this same timer is used, but two parameters you need to configure for a PWM. One is known as time period, another one is known as duty cycle. So here duty cycle is nothing but the on time of the time period. So the duty cycle value we are storing in a register known as timer capture compare register. Timer capture compare register CCR. So whenever the timer value is reaching the capture compare register, so let us take this is a PWM which is being generated, and PWM is generated in a pin known as OCX. This X stands for the PWM or timer channel. This X stands for the timer channel or PWM channel. So if you are configuring PWM1 in timer channel 1, OC1 pin will be there. Output compare pin will be there. PWM is generated in the same compare mode of operation of timer. In one of the lecture we have seen how the compare mode of timer can be configured in a timer, right? So In the same output compare register mode of operation PWM is generated, and since PWM use output compare mode, PWM will be generated in a pin known as output compare pin. So X stands for the timer channel. So if we are configuring timer 1 channel 1, OC1 pin will be used for generating the PWM output compare 1 channel. So, and we can configure the PWM as active high. So what do you mean by active high? Before starting of the PWM pin will be in logic high state, and whenever and the counter will keep on incrementing. Whenever the counter reaches equal to the value stored in CCRX, X is the channel. So whenever the timer counter value becomes equal to CCR value, this OCX pin will be set to low or reset. And again timer will be keep on incrementing, and when the timer reaches the auto reload value, the timer pin will be, or OC1 pin will be set. So whenever the timer counter value is equal to CCRX pin, PWM pin will be reset, but the timer keep on counting, and whenever the timer value is equal to auto reload register value, it will set. This is how the PWM is generated. So here you can see that the on time of the PWM is decided by the CCRX value. If you are reducing the CCRX from here to here, you can see that on time will be reduced, because if you are drawing a line here, let us take CCRX is configured in this value, so the line will be here. So instead of making PWM pin low here, it will be made as low here, right? That means by configuring the CCRX value, you can configure the duty cycle or on time of the PWM. And how will you configure the time period? Let us take this is one time period. So how will you configure the time period? By changing the auto reload value. If you are reducing the auto reload value, what will happen? Now at this, let us take in this point, PWM is set. If you are reducing the ARR value to somewhere here, the PWM will be set at this point, right? That means if you are measuring the time period from here to here will be the time period. So time period will be reduced. So by changing the value stored in auto reload register, we can vary the PWM time period, and by modifying the value stored in capture compare register X, we can modify the duty cycle. So these are the two registers which is used for storing time period and duty cycle or on time for PWM generation. So since you are using timer for generation of the PWM, we need to configure timer X prescaler. So for time being, I am going to configure the PWM in timer 2 channel 1. Right? So I am going to configure PWM in timer 2 channel 1. So timer 2 prescaler can be configured by PSC, as you have seen in the previous timer video. So let us take, if you want to configure a prescaler ratio 1, what should be the PSC value? Prescaler ratio minus 1. So if you want to configure a prescaler ratio as 2, what will be the PSC value? 2 minus 1, that will be 1. So whatever prescaler ratio you need to have, that value minus 1 should be stored in PSC. So the frequency of the clock given to the input of prescaler divided by PSC value plus 1. This is how the prescaler equation is working. Whatever input frequency is given as an input, that will be divided by PSC plus 1. PSC plus 1 is nothing but the prescaler ratio. So you need to configure the prescaler ratio here also, since we are using timer. Then this also we have seen, these are the prescalers associated with the timer 2, right? So we have seen that timer 2 is connected to APB1 prescaler or APB bus interface. Timer 2 is connected to APB1 bus interface. So you can configure APB1 prescaler and APB1 is again connected to AHB bus. So we can configure AHB prescaler also. But in the APB1 prescaler, you need to keep in mind, for all the other peripherals, APB1 prescaler can be 1:1, 1:2, etc. up to 16. But for timer peripheral, APB1 prescaler can be either 1:1 or 1:2. We cannot have 4, 8 or 16. And what is the function of a prescaler? If you are giving an input to a particular prescaler, if it is configured configured it in 1:1, it will get 1 clock cycle at the output. When you are giving 1 clock cycle input, you will get 1 clock cycle at the output. If the prescaler ratio is 1:2, if you are giving 2 clock cycles at the input, you will get 1 clock cycle at the output. So for the timer 2, we can configure AHB prescaler, APB1 prescaler and timer 2 prescaler. The input to the timer will be high speed internal clock. That is nothing. High speed internal clock is given as a clock source for system clock. It is nothing but 16 megahertz. So these are the prescalers that can be configured for timer. So the same prescalers are used for the PWM generation also. And next one, we need to find out which pin is mapped onto timer to channel 1. Because if we know the actual pin of timer to channel 1, then only we can identify where the output will be generated. So here in this table showing the alternate functions, we can see that PA5 alternate function 1 is nothing but timer to channel 1. So if you want to generate PWM in channel 1 of timer 2, PA5 should be configured with the alternate function 1, because PA5 is having alternate function as timer to channel 1. So the next step is you need to configure PA5 with a alternate function 1. So what will be the first step? First step, in order to configure PA5 as alternate function 1, you need to configure the mode register with the alternate function mode. Right? You need to configure the mode register. So before configuring the mode register, you need to configure the clock to the particular GPIO peripheral. Why? Because timer to channel 1 is a functionality that will be configured on PA5. So the GPIO port A should be connected to the clock, or clock should be enabled for GPIO A. That is the first step. How will you enable that? AHB1 enable bit 0 should be set as 1. So 0th bit of AHB1 ENR should be set as 1 in order to enable clock for GPIO A. Second step is you are going to configure the mode selection register. Mode selection register is used to configure the function of a particular pin. So here I need to configure PA5. So you need to select GPIO A mode selection register. And for configuring each pin, 2 bits of mode selection registers are used. So here, since I need to configure PA5 as timer to channel 1, bit number 10 and 11 should be used. And PA5 is represented here directly, mode 5. That means these 2 bits are used for configuring the mode of PA5. And if you are writing these 2 bits are 0, 0, PA5 will be configured as input, 0, 1, it will be configured as output. But in my case, I need to configure alternate function 1 for PA5. Why? Because from this table you can see that PA5, if it is having alternate function 1, then it will be acting as timer to channel 1. So we need to write 1, 0 to bit number 11 and 10. If you are writing 1, 0 to mode selection register, bit number 11 and 10, PA5 will be configured with alternate function mode. So if you are configuring with alternate function mode, then only in the next step we can configure which alternate function should be there for that pin. Right? So here you are configuring PA5 with alternate function mode. That means bit number 11 should be 1, 10 should be 0. How will you do that? PA5 and equal to tilde of 0, 0, 0, C00 means bit number 10 and 11 it is cleared. And in the next step, OR equal to 80 means bit number 11 is 1, 10 is 0. 1, 0, 0, 0 means it is 8. So here bit number 10 is 0, 11 is 1. So when you are writing OR equal to 800 means you are configuring PA5 with the alternate function mode. Which is alternate function mode? Which alternate function mode you need to select? Alternate function 1. That will be configured in the next step. Here we are configuring PA5 in alternate function mode, writing 1. Which alternate function will be seen in the next register. So how will you configure the alternate function? What type of alternate, which alternate function you need to configure? For that, two registers are used. One is known as alternate function register low, alternate function register high. Alternate function register low is having 32 bits. It is used for configuring the alternate functions of pin number 0 to 7. Total 16 alternate functions are there. Similarly, alternate register high is used for configuring the alternate register function of pin number 8 to 15. So here also total 16 alternate functions are there. So based on which pin you need to configure, any of this register should be configured. I need to configure PA5, so alternate function register low should be configured. And if you want to configure this alternate function register, before that the mode selection register should be configured in alternate function mode. That is why we are writing 10 to mode selection register. So that we have done in the previous step. We have written 10 to corresponding mode. Then only I can configure the alternate function registers. So here I need to configure alternate function for PA5. So I am selecting alternate function register low. And 4 bits of the alternate function register is used for configuring the alternate function for a particular pin. So 0 to 3 is used for configuring alternate function for PA0. Similarly, here I need to configure alternate function for PA5. So I am going to configure bit number 23 to 22. These 4 bits are used for configuring alternate function for PA5. That is why this bit name is given like this, AFRL5. And which alternate function you need to configure? Alternate function 1. From where do you get that idea? From this table we have seen that PA5, if it is configured with alternate function 1, it will be having a functionality timer to channel 1. That is why alternate function 1 should be configured. How will you configure that? Bit number 23 to 20 should be written with 0001. So alternate function low register bit number 23 to 20 should be written with 0001. Right? So initially we are clearing these 4 bits. So when you are writing AND equal to tilde 00F00 means you are clearing these 4 bits. In the next step, AFR 0 equal to or equal to 1000 means 23 to 20 you are writing 0001. That means you are configuring PA5 with alternate function 1, that is timer to channel 1. And why the 0 is given? 0 is shown that AFRL you are configuring. When you are configuring AFRH, if you are configuring from pin numbers 8 to 15, then AFR1 will be shown. So this 0 or 1 represents, this 0 represents the AFRL. Then next step we need to configure the capture compare mode register. This register also we have seen while we are dealing with the compare mode of operation of timer 2. So in capture compare register 1 you are configuring the bits for channel 1 and channel 2. So from 0 to 7 is used for configuring channel 1. So in all the bits you can see 1 is there because it is used for configuring channel 1. From 8 to 15 these bits are used for configuring channel 2 of timer. So 2 is there in each of the bits. So in my case I am going to configure timer to channel 1. So bit number 0 to 7 of CCMR1 I am using. If you are configuring channel 3 and 4, you need to use CCMR2 register. So CCMR1 is used for configuring channel 1 and 2. CCMR2 is used for configuring channel 2 and 3. Here I am taking CCMR1 0 to 7 since I am configuring timer to channel 1. So this timer X represents the timer number, and here this represents CCMR1 represents the register for configuring channel 1 and 0. So in this part we are going to configure for channel 1, and bit number 4 to 6, this is known as output compare 1 mode register. Output compare, why it is 1? It is the output compare mode bits for channel 1. And this mode, output compare mode, should be configured with PWM mode 1 because we are going to generate PWM. In the previous example where compare mode of operation is used, we have written these bits as 0, 1, 1. That means the output pin will be toggled when timer counter is equal to CCR1. But here in my case I need to generate PWM, so the output mode selection bit should be 110. That means mode 1, PWM mode 1. PWM mode 1 and PWM mode 2 both are the same. Only one difference is that if we are configuring PWM mode 1, before starting of the PWM pin will be active high or in logic 1 state. Logic 1 means in the waveform you can see here before starting of the PWM pin is in logic high. This is known as active high state. If you are configuring PWM 2 mode, instead of making it in active high, it will be in active low. So for time being, I am configuring PWM mode as PWM mode 1. So bit number 6, 5 and 4 should be 110. That is why I am writing CCMR1 equal to 0x60. 60 means 0, 1, 1, 0. So bit number 6 to 4 it will be 110. 110 means PWM mode 1. Then in the same CCMR1 register, we are configuring bit number 3. It is used for configuring output compare 1 preload enable. So preload enable means we are going to enable a preload register. We can enable or disable a preload register. Preload register is nothing but it is something like a shadow register. Normally the PWM counter value will be compared with the shadow register of CCR1, right? So whatever value you are writing to CCR1, if preload register is enabled, you will be writing only to the preload. We cannot write into the shadow register directly, right? So you will be writing to preload register, and whenever an update event is occurring, whatever value is written into the preload value register will be taken to actual CCR register. Right? What do you mean by update event? What do you mean by update event? Whenever the value is equal to timer counter value is equal to auto reload register, it will roll over to 0. That rolling over to 0 is known as update event. So whenever that reloading or rolling over to 0 is taking place, content of preload register will be loaded to CCR. That means whenever update event is occurring, then only CCR value will be changed. But in my case, I don't need that. In my case, whenever I am writing the value to CCR1 register, immediately it should take into effect. Right? Whenever I am writing to CCR1, directly CCR1 should be changed with the new value. So I am going to disable the preload register. So I am writing bit number 3 as 0. That means preload register is disabled. So when I am writing 60, that means the bit number 3 is 0. Preload register is disabled. Then in the same register, bit number 0 and 1, it is used for configuring the capture compare 1 register. That means whether you are going to configure the pin as a capture pin or a compare pin. In my case, PWM is also generated using capture mode. So I am writing 0, 0 in the capture compare 1 selection register. Right? So 0, 0 means CC1 pin, that is capture compare 1 pin, capture compare channel 1 pin will be configured as output. Because for the compare mode of operation, we are generating a waveform in the capture compare out in the pin. So whenever you are generating a waveform, that pin should be configured as output. So that is why I am writing 0 0 here. That means my CC1, that is capture compare channel pin, is configured as output. So again, when you are writing the 6 0, 0 0 is configured in these two bits. So by writing 6 0, all the three configurations are done in capture compare register 1. Then the next register is capture compare enabled register. So now we have configured the capture compare mode and other things. Next you need to enable the capture compare itself. So capture compare enabled register is used. In that bit number 0, I am making it as 1. Bit number 0 1, what does it mean? Capture compare 1 output is enabled. Then bit number 1, that is CCP 1 pin 1P, what is that? Capture compare output polarity. Output polarity you are making it as 0. That means before starting or generation of the PWM should be pulled high. Before starting, the PWM should be pulled high. So it is made as high. So you are writing 0 to this pin. So before starting, it will be pulled high. But you need to keep in mind, when you are configuring in PWM mode 1, how it will be working? By configuring the CCRX, you are configuring the on time, right? But if you are generating PWM in PWM mode 2, by configuring the CCRX, you will be configuring only the off time. Because if you are starting the PWM with the active low state, how the PWM will be generated? When you are starting with the PWM low, the PWM will be generated like this. Instead of this, it will be generated like this. If the PWM is in active low state, PWM will be generated like this. That will be the opposite of the PWM what you have shown in the figure will be generated. Right. So this is where the PWM is in active high state, but here PWM is said to be in active low. That means it will be starting with active low, then it will, whenever CCP R1 is matched with the counter, it will be set. It will be there in the set state itself, and whenever the counter value is equal to auto reload register, it will be reset. Right. So if the PWM is in active low state, when the counter value is equal to CCRX, PWM will be set, and when the counter value is equal to CCR, when the timer value is equal to auto reload value, it will be reset. In the case of PWM, if it is in active low state, active low. But in the waveform what it is shown, the PWM is in active high state. That means by configuring the CCP-RX, you are configuring the on time, right? You are configuring the on time if the PWM is in active high. But in the active low state PWM, by configuring CCP-RX, you will be configuring only the off time, right? So if the PWM is in active low, you will be configuring only off time. But if the PWM is in active high, you will be configuring the on time, right? So here for our example, we are configuring PWM in active high. So the on time we are configuring, right? And in the CCP capture compare enabled register, we are configuring the 0th bit. In the 0th bit, you are enabling the capture compare, and 5th bit you are configuring it as active high. Why active high? We are telling the controller that when you are starting the PWM, it should be in active high state. But if you want to generate this kind of PWM, you need to tell the PWM that you need to start PWM with active low. So since I am generating this active high PWM, you need to tell the controller that it should be configured in active high state. That is why in capture compare enable register, first bit, capture compare enable register, first bit is used for configuring polarity. I am writing it as 0 because my PWM is in active high states. Then the third bit of capture compare enable register, it should be kept as cleared. So these are the three configurations required for configuring the timer in compare mode of operation. In compare mode of operation, CCP NP should be cleared and this bit should be 0 as you are configuring active high, and the 0th bit should be 1 as you are enabling output compare. Then the next register is auto reload register. So we have already seen that auto reload register is used for configuring the PWM time period. It can be maximum 32-bit value based on the timer. So here, since I am using timer 2, 32-bit auto reload value can be specified, which will configure PWM time period. Then CCPR Y register, that is Y stands for the channel number and this timer X stands for the timer number. So I am configuring timer to channel 1. So CCR1 is used for configuring the duty cycle. So if you are configuring channel 1, CCR1 should be used. If you are using channel 2, CCR2 should be used. Channel 3, CCR3 should be used. Channel 4, CCR4 should be used. So CCR register is used for configuring the PWM duty cycle. Since I am going to configure timer 2 channel 1, I need to configure CCR1 register with the desired duty cycle. Then here we are going to see how or what value you need to load into ARR auto reload register and CCR1 register in order to generate a particular waveform, particular PWM with particular duty cycle and a particular PWM period. So PWM period can be calculated by using this equation. This equation is same as the delay calculation equation for timer 2, right? Because the total time delay taken by the timer is nothing but PWM period in our case, right? Because ARR is represented, it is used for storing the delay, maximum count value the counter can have. Whenever the timer is incrementing, you are giving a clock. So total number of clocks is stored in ARR into the time taken for one clock will give the maximum delay. So PWM time period is nothing but the value stored in ARR. That means the count value, that maximum count value it can have, right? That is nothing but the time period register into AHB prescaler into APB1 prescaler into timer PSC plus 1. These are the three prescalars into the time taken for one clock. So if the prescalars are not there, what will be the total time period? Auto reload register value, that is n into time taken for one clock. So if the auto reload value is 10, 0 to 10 it will increment. So 11 into time taken for one clock will give the total time taken. But here, since these three prescalars are there, that also should be multiplied. So here in my case, time taken for one clock is 1 by system clock. System clock is my input. So duty cycle is calculated by the equation on time by PWM time period. On time is represented or written in a register known as CCRY register. PWM time period is represented or written in TMRX auto reload register. Why this plus 1 is there? Because when the timer counter is incrementing from 0 to ARR, after reaching ARR it will roll back to 0. So when it is rolling back to 0, then only update interrupt flag will be set. In the case of timer 2, we have seen that. So the total ARR value count plus one cycle which is required for rolling back to 0 also should be taken into account here. That is why on time by PWM time period plus 1 is given. Then into 100% will give the duty cycle. So let us take an example where auto reload value, that is n value is 2666, the PWM duty cycle value is 8889 and the prescaler is set to 9. Provided these values, what will be the value of PWM time period, frequency and duty cycle which is configured by these values. We are assuming that AHP and APB1 prescalars are not configured, that is 1:1 prescalar is for these two, and the input clock is system clock as you have seen here. So by using these three values, how will you calculate the PWM time period? You can substitute these values in this equation. So ARR value is 2666, AHB and APB prescalars are 1 and 1, timer prescalar is P, that is 9 plus 1 into time taken for one clock cycle is 1 by system clock, that is 1 by 16 megahertz. When you are substituting all these things, you will get PWM period as 0.01666625. What will be the PWM frequency? 1 by PWM time period, that is 1 by this value, that is equal to 60 Hertz. Then how will you calculate the duty cycle? Substitute the value in this equation. CCRY is 8889, ARR is 2666 plus 1 into 100. So when you are substituting this value, you will get the duty cycle as 33.3. So from this example, what you understood? If you want to generate a PWM of 60 Hertz and a duty cycle 33.3, we need to load a value 2666 into ARR and 8889 to CCRY and PSC as 9, provided there is no prescalars, right? So if you are asked to generate a PWM of say 10 Hertz and a duty cycle of 50%, what you will do? The same equation you need to take. You need to substitute the frequency as 10 Hertz here, right? 10 Hertz you need to divide 1 by 10 Hertz you need to do. That time period you need to give here, right? And you will be configuring the prescalars 1, 1, and for time being you can give the prescalar as say 9 or 10, right? So after substituting all these values, there will be only one known timer to ARR, that is this value. So when you are substituting whatever Hertz PWM you need to generate, that time period if you are substituting here, you can find out the value of ARR. Similarly, you can substitute the frequency, that duty cycle. If I want to generate 50% duty cycle, in this equation, substitute this duty cycle as 50%. PWM time period you have already calculated from the previous equation, that you need to substitute here. So this and this will be known. You can calculate the on time. That value should be loaded in the register TIM CCRY, right? So how will you calculate the time period? How will you calculate the value to be loaded into ARR? PWM time period is known. Say if it is 10 Hertz, calculate the time period corresponding to 10 Hertz, substitute it here. Assume any prescalars for AHP1 and AHP and APB1. Then assume a prescalar for timer. You can take it as a 10 or 9. Then time taken for one clock is 1 by 16 megahertz. So this term that is AHB prescalar, APB prescalar, timer prescalar, time taken for one clock and time period is known. So since all these values are known and timer ARR value is only unknown, so you will get a particular value of ARR, right? So if you are moving that value to ARR, what does it mean? Whatever desired PWM, in my case if it is 10 Hertz, 10 Hertz PWM will be generated by configuring the value in ARR. Similarly, how will you calculate duty cycle? From here you got the value of ARR, so that you need to substitute here. Duty cycle is say I need to have a duty cycle 50%, substitute it here. So these two terms are known, only the CCRY is unknown, right? So when you are substituting this and calculating, you will get the value of this. So that value if you are moving to CCRY, 50% duty cycle will be configured. So by configuring TIM ARR and CCR, you are configuring the time period and the duty cycle of a PWM, right? So by calculating this value should be given to ARR and this value should be given to CCR in order to generate a 60 Hertz PWM with the 33.3 duty cycle. Then after configuring all these steps, the last step should be you need to configure the timer control register, right? So in timer control register, only 3 bits you are configuring. 0th bit is counter enable. So once all the timer and capture compare configurations are over, then only counter should be enabled as the last step. We are making this bit as 1. Then third bit is 1 pulse mode. Here 1 pulse mode means timer will increment from 0 to ARR and it will stop. But in my case I don't need that. I need to keep on counting. Again it should be starting from 0 onwards. So I am disabling 1 pulse mode. So I am writing 0. That means counter is not stopped at that update event. It will keep on counting. So I am writing 0. Then the fourth bit is direction. Here I need to configure the timer to count in upward direction. Then only timer will be incrementing from 0, 1, 2, 3 etc. up to ARR. So the direction I am configuring it as 0. So bit number 4 is 0, 3 is 0, bit number 0 is 1. So when I am writing timer CR1 equal to 1, that means you are enabling the counter. These two are direction is up counter and the update event it is disabling the 1 pulse mode. So this should be the last step. That means you are enabling the timer after all the other timer configuration. So these are the steps required for configuring PWM mode of operation or PWM generation using STM32F446. So now we are going to see the program corresponding to the explanation what we have seen till now. We are going to generate a PWM in timer 2 channel 1. That is nothing but PA5 pin. So what is the first step? We are writing AHB1 ENR equal to 1. That means you are enabling the GPIO clock by setting 0th bit of AHB1 ENR register. Then you are going to configure the alternate function mode for PA5. For configuring alternate function for PA5, these two steps are used, that is OR equal to 800. That means PA5 is configured with the alternate function mode. Then which alternate function you need to configure, that is configured by using this step. So AFRL register, you are writing OR equal to 1000 means you are configuring PA5 with alternate function 1. Alternate function 1 is nothing but timer 2 channel 1. So alternate function 1 is nothing but timer 2 channel 1. It is configured on PA5 by using AFRL register. L is represented by this 0. Then from here onwards you are configuring the timer 2. So first of all you are enabling the clock to timer 2. How will you do that? APB1 ENR equal to 1. Previously it was AHB1 ENR for enabling GPIO. Now it is APB1 ENR 0th bit you are setting in order to enable clock for timer 2 because timer 2 is connected to APB1 bus interface. Then I am configuring the prescaler as 9. In the previous calculation I have taken the prescaler as 9. So for a generalized representation we are writing it as 10 minus 1. Why this minus 1 is there? Because PSC is nothing but actual prescaler ratio minus 1. So I am configuring my actual prescaler ratio as 10. So 10 minus 1, that is 9, should be moved on to PSC. If you are moving 9 to PSC, my actual prescaler ratio is 1:10. Then I am configuring ARR as 26667 minus 1. Why this minus 1 is there? Because if you are writing 26667, the counter will be incrementing from 0 to 2667. For time being, we can consider ARR as 10. So if you are giving ARR as 10, what will happen? Timer will be incrementing from 0 to 10. That means for counting from 0 to 10, each count will take one clock. So for counting from 0 to 10, total 11 clocks will be taken. But I need only 10 clock. Since you are incrementing from 0 to 10, 11 clocks will be taken. But I need only 10 clock. So what should I do? Whatever value you are moving to ARR, minus 1 should be given. So my actual value should be from only these many count should be there, 2667. How will you get 2667 count? You need to count from 0 to 2666. If you are counting from 0 to 2666, we will get total 26667 count. So 2667 minus 1 should be given here, so that you will be counting from 0 to 26667. Then you are initializing the counter value with 0. You are initializing the counter value with 0, initializing the counter. Then CCMR1 you are writing 60. That means you are configuring the output compare in PWM mode. Then the other two configurations also you are doing. For more details, you can go through the explanation of the PPT for the details regarding CCMR1 configuration. Then next step, you are configuring capture compare enabled register. You are writing it as 1. That means 0th bit you are setting. 0th bit stands for you are enabling PWM or you are enabling channel 1. For enabling channel 1, 0th bit you are setting. Then you are configuring the duty cycle in CCR1 register. Why CCR1? 1 stands for the channel number. So CCR1 we have configured, for the calculation we have taken 8889. Again 8889 minus 1 should be given, because CCR1 also it is counting from 0 to that value. Right. So since it is counting from 0 to that value, whatever value that you need, minus 1 should be given. Then only the total count required for the duty cycle will be this value. So that value minus 1 you need to give. So this is used for configuring the duty cycle, and this is used for configuring the time period. And once all the configuration is over, as the last step you need to make CR1 equal to 1. CR1 equal to 1 means 0th bit of CR1 you are setting. 0th bit, what is 0th bit of CR1 representing? It is used for enabling the timer. So as the last step you are enabling the timer. So with the configuration what you have made here, the PWM will start generating automatically. That is the advantage of using this. But if you are going to generate a waveform using timer 2, you need to check for update interrupt flag. The CPU should check for that flag. Then you need to change the waveform, you need to change the pin status, and so that the accuracy will be affected, time taken will be affected. But here, once you are configuring the duty cycle and the time period register, PWM will be generated based on the PWM frequency and duty cycle what you have calculated. Right? PWM will be generated automatically according to the duty cycle and period. So we don't need to do anything. So the last statement should be simply a while one. Why this while one is used? In order to prevent the program execution to start from this line onwards, right? Because these are the configuration steps. These steps should be executed only once by the processor. That is why we are giving an infinite loop here. That means this is known as a short jump. You are preventing the processor to go and execute these lines again and again. So once this configuration is over, PWM will start generating its own. So this is how you are writing a program for generation of a PWM in timer 2 channel 1.